Students, in this video we'll discuss the trace of a matrix. Let's consider a square matrix A. We'll assume that this matrix is n by n, and so our matrix A will have the form A, I, J, where I and J go from 1 up to n. We're going to define the trace to be the sum of the diagonal elements of this matrix. Define the trace of A to be the sum, J goes from 1 up to n, of A, J, J. That's just the sum of the diagonal entries. So this is the sum of the diagonal entries of A. Okay, great. Let's talk about the basic properties of trace. There are 3 trivial properties of trace which are easy to check. So these are basic properties of trace. Basic properties. Property number 1 is that the trace of A plus B, and this assumes, of course, that they have the A and B have the same dimension, otherwise I couldn't add them together, right? The trace of AB is the trace of A plus the trace of B. Okay, and that's easy to see too, because if I look at A plus B, so A plus B is simply just Aij plus Bij, where I and J go from 1 to n, and I see that if I look at when I is equal to j, I just have Aij plus Bij, which is going to be the trace of A plus the trace of B. So it follows from this relationship over here. Second important property is similarly by the linearity. So I have the trace of any multiple k times A is just going to be k times the trace of A. And that, of course, just follows from what fact? That just follows from the easy fact that if we look at Ka, then Ka is the matrix K times Aij, where I and J go from 1 up to n, right? And so the diagonal elements over here are just K times A11 plus K times A22, etc., K times ANN. And so we get this result from this formulation over here. All right, great. What's the next relationship? This is slightly more non-trivial, that the trace of A is the same thing as the trace of A transpose. And that's, of course, because the diagonal is an invariant when you transpose. Okay, so the proof of this fact stems from the fact that proof of this fact is that the diagonal elements of A are invariant under transposition. Okay, great. Those are the most elementary properties of trace. Now let's return to some of the more non-trivial properties of trace, and the fact that the trace of A times B is the trace of B times A is the first one of these things. So here's a proposition. The trace of A times B is equal to the trace of B times A, right? I'm assuming here that A and B are n by n matrices, right? And so, of course, what is the ij entry of A times B? So if we look at A times B, for example, the ij entry of this thing, A, B, Ij, the ijth entry of this matrix over here is going to be what? It's going to be the sum over K. K goes from 1 up to n. And then what? And then I'm going to have an A, Ik, and then a B, K, J. Great. All right, and then of course when we're going to sum, when we do the trace of this thing, I'm going to sum over A, B, I. So the trace, for example, of A, B is going to be the sum. I goes from 1 up to n. And I'm going to replace I with J. I'm going to write like this first. A, B, I, like so. And then this is going to be the sum. I goes from 1 up to n. And then what is A, B, I going to be? It's going to be the sum. K goes from 1 up to n of A, I, K, and then B, K, I, because I replaced J with I over here in this formula. So that's the trace of A, B, right? Now let's look at B times A, right? So if I look at B times A, well, what will B times A, I, J be? B times Aij will be the sum over K. K goes from 1 up to n of now B the B, I, K, and then A, K, J. And so by the same reasoning over here, what will the trace of BA will be the sum over I going from 1 to n, now I and j are going to be equal, of B, A, and then I, right? I. And just, well, I put a comma over here. We don't need the comma technically. Okay, now what is the I entry? I'm going to fill in what this thing is over here. This is going to be the sum. I goes from 1 up to n. The sum, K goes from 1 up to n, of what? Of B, I, K, and then A, K, I. Now let's look at these things carefully over here. You might say, wow, these things are completely different over here. This thing over here, these terms over here in my sum, and these terms in my sum are completely different. But all I need to do to prove that these two expressions are equal to each other, so these two expressions are equal to each other. Those are equal to each other, so big equal sign over here. Those are equal to each other. Now what happens over here? If I change the role of I and K, if I switch the role of I and K, if I change the indices, we see that these things, the K will go over here and the I will go over here. The K will go over here and the I will go over here. So I just change the roles of I and K. So if we change the roles of I and K, we see that those expressions are equal. So in fact, we've just proven that the trace of AB is the trace of B times A. Okay, great. All right, excellent. And so there's a cool consequence of this. The cool consequence of this is that, as an immediate corollary of this, is that there are no matrices. There are no matrices A and B such that AB minus BA is equal to what? Is equal to the identity matrix. Why not? Because I can just trace this identity. So the proof of this is just if you trace, the trace of the left-hand side of this inequality is going to be equal to the trace of AB minus the trace of BA, which we know is equal to 0. And the trace of the right-hand side, I'll say this is the n-by-end identity over here, where there are n-by-n matrices. The trace of the right-hand side, well, the identity matrix says 1's along the main diagonal, and there's n terms on the main diagonal, so the trace of the right-hand side is equal to n. So if n is not equal to 0, so if these things were equal to each other, there are no matrices for this to happen. So I would conclude if there were matrices for which this would happen, then n would be equal to 0, which is a contradiction over here. That's a contradiction, and that proves that there are no such matrices such that A times B minus B times A is equal to the identity matrix. The last proposition we should at least mention is this is actually as a consequence of this sort of formulation over here, right? Is that the last proposition is that the trace of A transpose is just going to be the sum over I and J going from 1 up to n of A, I, J quantity squared, right? It's just the square of all the entries. It's the sum of the square of all the entries in the matrix over here. And we can easily see this by looking at this formula over here. If I just replace B over here with A transpose, then this becomes just an A, J, K. I'm summing over K over here. And then when I replace I and J, you see we're going to sum over all the possible entries in the matrix. So this formula over here, that the trace of A transpose is equal to the sum of the square of the entries of the matrix, is going to be important in further applications. And we'll see further applications of how the trace is going to come up when we're studying eigenvalues. One particular example of that is the fact that the trace of a matrix is equal to the sum of the eigenvalues of the matrix. And so we'll use that property in further videos to exploit spectral properties of matrices, and that's going to be a very useful invariant when we're discussing matrices and different factorizations. Thank you very much.